Okay, so we're going to be looking at exploring overall patterns of data and using large numbers of observations and creating curves and then gathering information from that today. So the first thing we're going to look at is what a density curve is. So we've got a bunch of examples here of density curves. So some characteristics of a density curve is that it is always on the x, always on or above the x-axis. Okay, and a density curve has an area under it that is going to be equal to 1. What we mean by that is if I had a curve here and I shade the area underneath it, that area there is going to be equal to 1. The density curve describes the overall pattern of the distribution, and the one that we're going to focus on, we'll use some others in the second semester, but the one we're going to focus on right now is the normal curve. And actually, let me go back and capitalize this. You will see normal capitalized usually because it's distinct. Doesn't mean normal in the sense that this data is typical data. It means normal in its pattern of distribution. So if we look at these two density curves down here in the bottom right, okay, we can see on the A is, so this was on a vocabulary test score in Iowa, the Iowa Test of Basic Skills. And so it tells you here that the portion of scores less than or equal to 6 in the actual data is 0.303. So that's what you're seeing here on the left. Okay, so based on the histogram, based on the data from the histogram, that is the proportion of scores that is less than or equal to a 6. If I used my density curve here and I measured the area here under the curve, okay, I get a proportion of 0.293 of people that have a score of 6 or less. So your density curve is very close. Okay, it's very it's pretty accurate. It's pretty close in getting, so we can use it to quickly estimate proportions and values. So when we're describing a density curve, we can describe the median as well as the mean of a density curve. So the median of the density curve is what we would call the equal areas point. So basically, you're trying to find the point where on either side of that point, you're going to have equal area under the curve. So for a density curve that is approximately normal shaped or symmetrical, like this one here, okay, the median is going to be right there in the middle. And I'm going to have 50% of my area is going to be on this side, and 50% of my area will be on this side. So in the curve next to it here, this one here that is skewed to the right, okay, my 50% curve, my 50% point here, my equal areas part, means I've got 50% of my curve on that side of the line and 50% on this side of the line. And if you'll notice, our mean and median are the same in my symmetrical curve, but they are different here in my skewed curve. And we've talked about this. Remember, our mean is our balance point. And so that's not always an equal area point if I have a long tail. Okay? If I have a long tail, I need to scoot a little bit closer to the tail to be able to balance the curve. And so my mean is my balance point, and my median is my equal areas point. You can see the mean illustrated down here at the bottom. So this data is right skewed, like the one above. Okay? And you can see as you shift the balance point around, the mean around, okay, the curve is not balancing. So you're looking for, again, the mean is the point at which the curve would balance. Okay, which in an asymmetrical curve is not going to be at the median. It's not going to be at the 50%. It's not going to be at the equal areas point because, again, the tail will throw it off balance if you put it at the same spot. So remember, when you're looking at a density point, okay, your mean for skewed data, your mean is going to be further down the tail than the median is. So for right skewed data, your mean would be larger than your median. And for data that is left skewed, right, for data that's left skewed, my mean is going to be further down the tail, so my mean will actually be smaller than my median. This would be my median, this would be my mean. So let's look at this a little bit further. So we have a density curve here, and our first question here is asking us to explain why this is a legitimate density curve. So thinking back to what we said made it a legitimate density curve, it had to be on the x-axis, had to be on or above the x-axis, okay? Basically meaning that all the values here had to be positive. And so it meets that criteria. So here's my x-axis here, and all my values are on or above it. Okay, so it is positive. So that would contribute to it being a density curve. It also has a total area of 1. And having a total area of 1 is another condition of a density curve. So both of those things make it a density curve. The legitimate density curve. Area of 1, everything is on or above the x-axis. So the second question here is asking about what proportion of observations lie between 7 and 8. Okay, so if we're looking at what proportion of observations lie between 7 and 8, the proportion is equal to the area under the curve. Okay, and so we'll be able to calculate this later, but it was given to us that the area under the curve here between 7 and 8 is 0.12. So the proportion is 12%. So the area under the curve is equal to the proportion. Okay, think back to what we saw earlier with the two density curves side by side. Okay, by calculating the area under the curve there, we got the 0.293%. That would be scoring a 6 or less. This is the same concept. I'm just using this little wedge of the curve here instead of the whole thing. Number 3 asks you to trace the density curve onto your paper and mark the approximate location of the median. Okay, well, remember our median is our equal area point. So you're looking for the spot where it would be equal, you'd have equal area on both sides. Our data is not completely symmetrical, it's slightly skewed. Okay, so our median would be pretty close to the peak, probably about here. Okay, that would be my median. And so number 4 is asking to mark the approximate location of the mean. Okay, and so in this case, I'm slightly skewed to the left. So remember, my mean is going to be just down the tail from my median. Not very far, because I'm not very skewed. Remember, my mean is affected by my outliers, right? And so these guys right here are going to pull that mean. But I don't have any super outliers that are way out there. So they're just going to pull it a little bit. So my mean would be more in here, just down the tail from my median. So the mean would have a lower or smaller value than the median. Okay, so let's look closer at a normal distribution curve. So this is a type of density curve, right? And again, it has what we call a normal distribution. Okay, so the normal is always going to be capitalized. These curves are always described by their mean and their standard deviation. So when we're describing the mean of a normal curve, we use mu. So this describes the mean of a normal distribution, and sigma here describes the standard deviation of a normal distribution. So if you draw or sketch a normal distribution curve and you're asked to show your work, and so you draw your curve, you identify your curve with a capital N, and then you give the mean and you give the standard deviation of that curve, like that, in parentheses. Okay, and so all of your normal distribution curves that you illustrate need to have this big capital N, parentheses, the value of the mean, the mu, comma, and then the standard deviation value, the sigma. That is a comma. Oh, that didn't help. So that's how you label or identify all of your normal distribution curves. So all of your normal curves are going to have this same basic shape. They're going to be symmetrical. Okay? They're going to be symmetrical. They're going to have one peak. And they're going to be bell-shaped. Okay? Those are the characteristics of a normal distribution curve. Okay? The wider the curve is, like this one here on the left, the wider the curve is, the larger the standard deviation, the larger variability that you have. Okay, so you have more variability the wider the curve is. The more narrow the curve is, the smaller the standard deviation. The mean is located there at the center of the peak. And so looking at the shape of the curve, again, how wide or how narrow it is, can give you an idea of the standard deviation. It can give you an idea of whether it's larger or smaller. It can give you an idea of the spread. So you can actually estimate the standard deviation of a normal curve by paying attention to where the curve starts to change. Like as you're going down, 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 down the curve, as it starts to change and curve back up at those inflection points in calculus. If you haven't had calculus, no worries. Okay, so where it's changing here and it's the slope is starting to flatten out, okay, that is one standard deviation away. If you look at these, like this curve up here at the right, okay, right here is where it starts to flatten back out. Same with right here, okay, in the middle of that curve where it starts to flatten back out. So if you had to, you could estimate the standard deviation based on that. So let's look at what we call the empirical rule and see how this can help us and we can get some more information from these curves. The empirical rule is this 68, 95, 99.7 rule, okay, and that is going to apply to our data points. What this rule states or means is that 68% of our data points, you can see this over here on the curve that's green and blue here, 68% of our data points fall within one standard deviation of the mean. So we have our mean plus or minus one standard deviation. That gives us 68% of our data points. Okay, 95% of our data points fall within plus or minus two standard deviations of the mean. So I take my standard deviation and I would multiply it by 2 and I would add it to my mean and I'd get this distance right here. And that would be 95% of my data points. And then the 99.7% of my data points are going to fall plus or minus 3 standard deviations away from the mean. So out here I get 99.7% of my data points. So looking at this curve over here on the right, okay, the curve over here on the right, again, is from that data, from that Iowa basic skills test. Okay, and the question that was asked around this is, would it be unusual for a student to score, a 9.94? Is it unusual to get a score above a 9.94? So a 9.94 out here, okay, a 9.94 is 2 standard deviations away. Okay, so if I know that 95% of my data points fall within 2 standard deviations, and I want to know the likelihood that they're going to get a score above that. So basically what I'm asking for is the area right here in this tail. Okay, well, my area under the whole curve is 1. Remember, so 1 minus, not equals. So 1 is my area under the whole curve. 1 minus 0.95 gives me 0.05. But then I only want this tail, right? what the 0.05 is both tails, but I don't want that tail. I only want the one here on the right. So when I divide this by 2, now I get 0.025, which is 2.5%. So it's a little unusual for somebody to get a score of a 9.94 or higher. That's only 2.5% of the scores. Okay, so let's look at another example with this. So our problem here is the distribution of the Iowa Test of Basic Skills Vocabulary Scores for 7th graders in Gary, Indiana is capital N, 6.84, and then 1.55. Remember what that tells us when I see this. That's how my curve is identified, meaning that my curve, because all normal curves have that same basic shape, okay? This means that my mean is at 6.84 and my standard deviation is at 1.55 for this particular normal distribution curve. So question A there wants what percent of ITBS vocabulary scores are less than 3.74, and it asked me to show my work. So when we draw this down here, so it's recommended that anytime you're solving one of these problems that you draw out your normal distribution curve. So it's been drawn here and went ahead and used these so you can see it down here. So we're finding the percent of scores that are less than 3.74. So remember my mean again was 6.84. You can see that right there in the middle. Okay, and 3.74 is 2 standard deviations below my mean. Okay, well, remember my mean here. So I would find that. Let's back up a little bit for a second. So I found that score. Well, I know that because 6.84 minus 2 times 1.55 gives me 3.74. So that's how I was able to draw this curve. Okay, I added 1 standard deviation to my mean here. I added 2. I added 3. I subtracted 1, subtracted 2, subtracted 3 standard deviations, and then was able to draw my curve from there. Okay, and so based on my empirical rule here, if I know that 3.74 is 2 standard deviations away from the mean, again, now this time I'm looking for this left-hand side tail, but I'm looking only for that left-hand side tail. I am not looking for the upper tails, the upper tail. I'm not looking for the tail on the right. So again, I've got my area under my curve is equal to 1. 95% of my data points fall between here and here. Okay, so what I have left over is 5% between this tail and the right-hand tail, but I only want one of those 2 tails, so when I divide by 2, I get 2.5%. Okay, and again, so we always answer in context. So I've shown my work, drawing your curve out and showing your work like this right here counts. Okay, what you need to do though is be sure that you labeled that curve, right, using your mu and your sigma. Okay, but then we need to answer in context. So we would need to state that about 2.5% of the ITBS vocabulary scores, because that's what we're talking about, are below 3.74. Okay, and so the next question then is asking what percent of the scores are between 5.29 and 9.94. Show my work. So once again, I've got the curve drawn out here. Okay, I used my plus 1 standard deviation, minus 1 standard deviation, drew it out. Okay, and it's asking me what percent of the scores are between 5.29, which is 1 standard deviation below, okay, and 9.94, which is 2 standard deviations above. Okay, so what I'm looking for is I've got 1 standard deviation covered. I've got from here to here. So I know 68% of my scores so far fall in there. But then I need one more chunk, right? And I know from here to here that I get 95% of my, 95% of my data points fall there. So when I do 95 minus 68, that gives me 27. And so what that tells me is that this chunk here and this chunk here are 27%. But like before, I only want one of those. I didn't go 2 standard deviations below. I only went 1 standard deviation below, but I went 2 above. So I need to divide this by 2. And I get 13.5. So now I know I've got 68% plus 13.5%, which gives me 81.5% of the scores. Okay, so use all my context. 81.5% of the ITBS scores are between 5.29 and 9.94. I need to define all of that out. What scores I'm looking at and what range I wanted, where I wanted it between, what percentage I wanted between which values. So let's look at a few more examples here. So we've got a distribution curve here. The distribution of heights of young women aged 18 to 24 is approximately N with a mean of 64.5 and a standard deviation of 2.5. Sketch a normal density curve for the distribution of young women's heights. Label the points 1, 2, and 3 standard deviations from the mean. Okay, so I know that I'm going to have, that was a terrible straight line. Actually, we'll use the bottom of the slide here. So I've got my normal curve here. My mean is 64.5, and I need 1 standard deviation above and below. So 64.5, and I need to do plus and minus 2.5. So 64.5 plus 2.5 gives me 67. I can estimate it again about where that would be, right at that inflection point. Okay, so 67, 64.5 minus 2.5 gives me 62. 2 standard deviations, so I need to calculate plus or minus 2 times 2.5. So 64.5 plus 5, so I get 69.5, and 64.5 minus 5, I get 59.5, and I need to go all the way out 3 standard deviations for my 99.7% of my data points. So 64.5 plus and minus 3 times 2.5, which would be 7.5. So 64.5 plus 7.5 gives me 72. And 64.5 minus 7.5 gives me 57. So what percent of young women have heights greater than 67 inches? Okay, so 67 inches falls here. So I'm looking for this. Oh, I should have labeled my curve. I didn't label it. So that my curve should look like this. That would be a better drawing of my curve. So for the second one here, I want to know what percent of young women have heights greater than 67. So again, a drawing is always good. So draw what I want. Well, I want this area right here. Okay, and so I'm looking for greater than 67 inches. Well, so let's look at how we can use this empirical rule in this curve to help us with this. So we know that from here to here is 68%. And now I'm left with this and this. So if I have 1, remember my area under my curve is 100% or 1. So 100% minus 68%, okay, that's going to give me 32%. So I know that this end and this end is 32%. And again, I only want 1, so 32% divided by 2 gives me 16% of young women have heights greater than 67 inches. So the next one asks, what percent of young women have heights between 62 and 72 inches? So now I'm looking at the area here between 62, and 72 inches. So I'm not going past, I'm not doing greater than, I'm just looking for this area right here in between. And so what I can do is I can use subtraction again, and I can basically figure out what this is and what this is and subtract it from 1. So we learned before that one of these little tails right here was 16%. Remember, we learned this before by subtracting so remember we got this from our 100 minus 68, right? This 68 right here, but I only want one tail, so I divide it by 2, right? And I get my 16%. Well, now I also know that from 57 here down to 72, I have 99.7% of my data points. So 100 minus 99.7% of my data points, okay, is going to give me the area of this tail and this dinky little tail down here, right? So that's going to be 0.3. Well, I only need the area of this tail here. I already took care of the tail on the left in the 16%. So this tail down here on the left was taken care of in this 16% that I calculated here. So I only need this tail on the right. So once again, I need to divide by 2. So now I get 0.15. So now I know that the areas basically that I don't want. So now I can do 100 minus 16 plus 0.15, which is going to give me 83.85% of my young women have a height between 62 and 72 inches. So that's the basics of normal distributions and the empirical rule. So next we'll look at standard normal distributions.